In this lesson, we'll look at graphs of sine and cosine functions and their properties. As we remember, a point traveling around the unit circle defines values of different trig functions, for example, sine, cosine, tangent, cotangent, secant, or cosecant, at the angle t, which opens from x-axis towards the terminal, passing through the point in the counterclockwise way. For special angles such as quadrantal angles or angles from special triangles, we already developed the values of the basic trig functions. For example, this table shows the values for sine and cosine. We are going to graph these functions, sine and cosine, on the x-axis if we assume that the angle t is actually positioned on a horizontal line rather than rotating around the circle. So to develop the graph of sine, we need to plot for every angle t the height of the point. That means the value of the y-coordinate of this point. And let's see how the shape of sine looks like on the following applet. This applet shows us 100 times sine rather than just sine, but consider rescaling this 100 for 1. The second function, cosine, assigns the value of x-coordinate of the point to every angle t. So the shape of cosine can be seen on the next applet. However, this applet is built a little bit differently. That means instead of looking at the angle from x-axis till the terminal and looking at this segment, they actually turn this terminal by 90 degrees, and they've been looking at the vertical segment because it's just easier. Since this angle is exactly the same as that angle, they've been just starting the angle from 90 degrees and opening it counterclockwise and then looking at the height. But the shape of the cosine is the same as they would start with the x-axis. It's just for the sake of making it easier to graph, so don't be misled by it. Okay, so we've seen both graphs. The curve of sine looked somehow like this, starting from 0, going up and then down and going back to 2 pi. That was the full period. And here's pi. So this is sine of t, or this is t. And it oscillated from -1 to 1. Obviously, the graph of this curve is actually proceeding farther in the same way, both directions. So it's kind of infinite wave like that, but we're going to look at just one period of it. The graph of basic cosine, though, it looks like this. Starts from 1 and going towards -1, and then going back towards 1 again. So here's the full period up to 2 pi. Now if we cut this period into 4 sections, 4 equal sections for both functions, then we end up with 4 quadrants. So those pieces correspond to quadrants. 1, 2, 3, 4. And the same for sine. 1, 2, 3, 4. That's cosine t. Similarly as for sine, cosine proceeds farther in the same way. So cosine looks exactly the same as sine, but it is shifted. Cosine starts with 1, sine will also have 1, but after 90 degrees, after pi half. This diagram also shows us the interpretation of values of other functions that we're going to talk about next lesson. However, you're welcome to justify to yourself how come this particular piece corresponds to the value of tangent. That one corresponds to the value of cotangent. secant is OR, that means this piece, and cosecant OQ, that means that piece. In this lesson, though, we will concentrate only on sine and cosine. So let's look at basic properties of sine. We already discovered the domain of sine is all real numbers. The curve can proceed farther both ways towards infinity. So for any real angle, we can always find the value, which is the height of the point on the unit circle. And notice how this graph was built. We've been looking at particular point, been looking at the angle that the terminal passing through this point is making with the x-axis. And for this particular angle, we've been marking the height of this point. So if this point was t, the height was this much. That's exactly the same part. If the t is higher, this one, then the height is higher. And then we've been drawing all those points, and the graph turns out to be such a wave. So domain is all real numbers. Range, since sine represents the height of the point, the height can't be lower than -1 and can't be higher than 1. So the range is from -1 to 1. Those are the most extreme points. 1 is here, -1 over there. Period. The full period is 2 pi, as we see, the full rotation, 2 pi. Symmetry. Well, if we extend the graph to the other side, it looks like the graph is symmetrical in origin. So the graph is odd, which really means that sine of -x is the same as negative sine of x. That's the definition of function being odd. And we already talked about those properties before, but now we can see them on the graph. Now, what's the y-intercept? There's only one y-intercept, which is just 0, 0. However, x-intercepts, in this case, they are called actually t-intercepts because on this axis we have t. Well, that doesn't matter if you call it t or x or theta, but in terms of t, that will be all the real t's, all real numbers, such that our number is of the type 0, pi, 2 pi, 3 pi, so any multiple of pi, k times pi, where k is an integer, double braced z. So those are all zeros or x-intercepts of the function. And what about cosine function? As I mentioned before, the way that this graph was obtained, it was slightly different than sine, but it's just for the sake of making it easier. Because if I make this angle here, that's the same angle as that angle over there, as long as these two terminals are perpendicular. And the length of the x-coordinate of this point is the same as the height, which is y-coordinate of that point. So what was done is to bring the x into the y and then place it here because it was easier to graph. So this piece is marked over there, and it actually represents the x-coordinate of the point that corresponds to the angle t. So that's how we obtain the shape of cosine. It starts from 1 going down to the -1 and back to 1. The properties of this function, again, domain is all real numbers, no problem here. Range is from -1 to 1, the same as for sine. Period 0 to 2 pi, so 2 pi. Symmetry, if we extend the graph to the other side, it looks like it's very symmetrical in the vertical axis. Well, we should actually call this vertical axis y rather than x, and our x is actually t. So the function y is cosine t. So as a matter of symmetry, the function looks like it's even. It's symmetrical in y-axis, so even. Which means that cosine of -x is the same as cosine of x. And we learned this before already. Now y-intercepts there's only one y-intercept, and this is 0, 1. As a matter of x-intercepts, or rather zeros, it is pi half, and then we can add any multiple of pi. So it's all real t's, such that t is of the type pi half plus k times pi, any multiple of pi, where k is an integer. And as I mentioned before, this full period is cut into 4 segments, 4 equal sections. Those sections correspond to 4 quadrants. So it's quadrant 1, 2, 3, 4. And similarly for sine, 1, 2, 3, and 4. Notice that our cast confirms here. Sine is positive in the first 2 quadrants, and it's negative in the last 2 quadrants, while cosine is positive in the first and the last quadrant, and it's negative in the second and third. Now we want to investigate how multiplying the basic function sine or cosine by a certain constant influence the graph. So if we want to graph 2 times sine x, we may start with the basic function sine in a full period from 0 to 2 pi and just multiply the function by 2. So the zeros will be kept at the same places, because 0 times 2 is 0, but the extreme values, for example 1, will be multiplied by 2, so it's stretched by 2. So the value here will be 2, and the value for negative 1 will become negative 2. So the graph will follow that road. This is the graph of 2 times sine x, so this is your function f of x, the yellow one. Second one, g of x, which is 3 times cosine x. Let's start with the basic function cosine x. It is on the second diagram. This is the gray curve, and we're multiplying it by 3. So the extreme values, instead of 1, they become 3. The zeros will be kept at the same place, but instead of negative 1 will be negative 3. And 1 times 3 is still 3. So our graph will look like this green shape. So that's our g of x. Now h of x, which is 1/2 cosine, well, all the extreme values will be multiplied by 1/2, still starts from cosine. So that's the shape. Instead of 1, it's 1/2. 0 is the same, and here's to negative 1/2, and back to 1. That's a full period. So the blue function is our h of x, 1/2 cosine. And we have one more function to graph, p of x, which is negative 2 sine x. Let's start with just basic function sine in the full period from 0 to 2 pi, that means up to here. To graph this shape, I suggest to cut the segment indicating the first full period into 4 equal sections. Those sections will be our quadrants, and put the quadrantal values. So at 0, sine is 0, at pi half is 1, then 0, then negative 1, and 0. And we need to connect those points. The curve looks somehow like this. That's our regular sine of x. Now to graph sine times negative 2, the zeros will be kept at the same places, but 1 will be multiplied by negative 2, so it becomes negative 2, and negative 1 times negative 2 becomes 2. Therefore, this curve is not only stretched twice, but also flipped to the other side. Okay, let's join these points, approximately like this. So this is the shape of p of x. Okay, so how can we describe what to do with the basic graphs of sine and cosine to obtain the new functions a times sine or a times cosine for any real number a? Well, what we really have done is stretching by the factor of 2 along the y-axis. So we need to stretch the basic graph by the factor of a in y-axis. If a is positive, the wave will be the same way. If a is negative, the wave will have to flip over the x-axis. So notice that this number in front of our functions really influence the height of the wave. And this height will be called the amplitude. So formally, the definition of amplitude is we're taking half of the difference between maximum and minimum values, which also indicates that amplitude is always positive because we subtract from the highest number the smallest number. So in this case, that was 2 minus -2 is 4, divided by 2 is 2. So that's the height. And in that case, the height is this maximum minus that maximum divided by 2, which is still 2. So this is the amplitude, here or there or there. Therefore, the amplitude of a sine x or a cosine x is actually absolute value of this coefficient a. So remember, we're taking absolute value of it. In this exercise, we need to recover the formula of the function given its graph. So how can we do that? First of all, we need to decide which section to take as a full period of the function. Here it looks like we should start from 0 and end on 2 pi. So the full period is actually 2 pi, and the shape is similar to sine, except that it's flipped. It doesn't go up, it goes down first. So this function, let's call it f of x, will have to have negative in front because of the flip. It will have something to do with sine of x. We just need to look at the amplitude. And to find the amplitude, we can look at this distance or we can look at that one. And this distance looks like it's 3/4 because up to here it's 1 and this is 3/4. So our function should be -3/4 sine x. In the second case, the full period looks like it's from 0 to 2 pi. That's a full wave, and it's a nice wave of nearly cosine, but upside down again. So let's call this function g of x. Therefore, the formula for our g of x should be negative because it's upside down. And what's the amplitude, this distance? Well, this is 1 and looks like a half. So it's 1 1/2, so it's 3/2 cosine x. In the following exercise, we want to investigate how the period is influenced by multiplying the input by a certain constant. Let's recall the facts from transformation of graphs that if we multiply the input by a certain constant, the graph will be stretched horizontally by the factor of reciprocal of this constant. So if we multiply x here by 1/2, the graph of the basic sine should be actually stretched by 2. And let's see on the diagram, if we start with the basic shape of sine, which is this gray curve, this is 2 pi, then sine of x/2 is actually the curve that stretches twice along the x-axis. So the new period, instead of 2 pi, it becomes 4 pi, because this point, when multiplied by 2, goes onto 4 pi, and point pi multiplied by 2 goes onto 2 pi, and point pi/2, which was corresponding to this, when doubled, will travel here. So yes, this graph is stretched by 2. Now if we want to graph g of x, which is cosine 2x, let's start with the basic cosine, which has a period of 2 pi, and those will be the quadrants. Cosine starts with 1, goes to 0, -1, 0, and 1. We join those points by a smooth curve. And now, to obtain graph of cosine of 2x, we actually multiply every single x coordinate of the important point of the basic graph by 1/2. So the value 1 happened originally for 2 pi, now it will happen for 2 pi divided by 2, that means by pi. So half away. This one will travel half away. This one will travel half away, and that one half away. So our final graph will look somehow like this. Obviously, we can graph another period here. So we'll actually fit 2 full periods between 0 and 2 pi. And those are the important points. Always keep the quadrantal points in place, so it will be easy for you to navigate how to graph this curve. So overall, we found out that the period of the new function sine b times x or cosine b times x, where b is any real number except for 0, can be found by the following rule. It is the period of original function, which in our case is 2 pi, divided by the absolute value of the constant b. Well, absolute value is because the period is always positive, so we are taking just the value of b, regardless of sign. And we can check how did it work in our cases. So the b in the first function, sine 1/2 x, was 1/2. Therefore, our period was 2 pi divided by 1/2, which is the same as 4 pi. And yes, we've got 4 pi here. In second case, the b was 2, and our period was 2 pi divided by 2, which is just pi. And yes, the period is pi from here to there. So that's very important rule to remember. Notice that if we know the period of the new function, we can also discover what the b is, because the b would be like 2 pi over the period that we know. Obviously, the b here could be up to the sign, but we usually take the positive part of it. In case the b is negative, we can always take the negative outside of the sine or outside of the cosine. We know how to do that. So we don't really have to worry about negative b at all. Okay, let's practice finding out the period and graphing functions with different periods. In first case, the b is pi, so the period by itself is 2 pi, because that's the period of sine, divided by pi, therefore that's just 2. So our graph should fit between 0 and 2, the full period of this graph. Okay, let's divide this segment into 4 equal sections and follow the shape of sine. That means starts from the midpoint, which is 0, towards 1, towards 0, -1, and 0 again, and connect those points as smooth as you can. If your curve is not perfect, that's okay, as long as you keep those points. So that's kind of structure that you have to have in order to get the proper graph. And the second graph, first find the period, which is 2 pi divided by this coefficient by the x, so by 2/3, which is 3 goes up, 2 will be cancelled, so it's really 3 pi. Okay, so the full period is from 0 to 3 pi. We need to divide this segment into 4 equal sections. Divide in half first, and then this half into another half. So it looks like that. Since this is negative cosine, so the regular shape of cosine that will normally look like this will have to be flipped. We start with -1, go towards 0, go towards 1, 0, and then -1. Keep these points and try to graph it. Here it is. And the other way around. This time we have a graph. We need to recover the function. So the first one, let's call it f of x. In order to find out the formula for f of x, I need to decide which section of the graph should I take for a full period. And it looks like if I take this section from here to there, that will be a full period of something connected with cosine. So it's a good idea to find out what is this period. And since I see that this period is equal to 6, then I can use it to find out the coefficient b that I need to multiply the x by. So b is 2 pi, the original period, divided by the period of the new function, which is 6. Okay, that means it's pi thirds. So now I can complete the formula for f of x. To cover the period, I will have to use cosine of pi thirds x, but we also need to accommodate for the amplitude, which was 2. So it's 2 times cosine pi thirds x. And finally, this graph. If I take the piece of the graph from here to there, that will be my full period. However, I have a problem. I don't know what this number is. It's not easy to figure it out from the diagram. So let's look for some other important points. Well, this one is also not easy, not a good one, but that one looks like straightforward. So this one corresponds to 2 pi, and we actually have 1, 2, 3 quadrants. So this is 3/4 of a full period corresponds to 2 pi. Well, let's make this calculation. 3/4 of a full period is 2 pi. So what's the full period? I need to multiply by reciprocal, so it's 8 pi thirds. Good. As soon as I have full period, I can figure out what's the b coefficient. It is the basic period 2 pi divided by the period of the new function, which is 8 pi thirds. Instead of dividing by 3, I can multiply by 3 in the top. So after reduction, I end up with just 3/4. So my b coefficient is 3/4. Good. If I call this function g of x, then the formula for g of x should be, okay, what is the shape? Looks like it's upside down sine, so it must be minus. What is the amplitude? Well, if this is 1, then this is 3/4. So minus 3/4 sine, and now the b coefficient is 3/4 of x. Here's the formula. You may want to plug it into the calculator and check. Obviously, watch the scale. And the last question asks us to graph the trigonometric functions involving some absolute values. So if you recall the process of transformation of graphs, you know that in order to obtain the final graph, it's a good idea to start with more basic graphs. So let's start with sine 2x first. We know how to graph this function. The period of such function will be 2 pi divided by 2, so it's just pi. Okay, so that will be full period. Those are the quadrants. And the sine looks like this. Joins these points. Okay, so that's the approximate shape of sine 2x. And we can draw another period, second period, here. And then the final graph, let's use red, we'll have to apply absolute value onto the yellow graph. That means everything that was positive stays in the same place. But if something was negative, now it will become positive. It will be flipped up. So we'll have bumps like that. So that's the final graph of our f function, the red one. Okay, let's try to do similar things for g of x. Start with 2 cosine pi x half. Let's graph this function first. In order to do that, it's a good idea to figure out the period. The period is 2 pi divided by pi half, which is the same as 4 when you flip and reduce the pi. So the period is from 0 to 4, and the 4 quadrants or here. So 2 times cosine, the amplitude is 2. We start with 2, go towards 0, negative 2, 0, and 2. It looks somehow like this. The next closer step would be function absolute value of 2 cosine pi x half in blue. So absolute value means that the part that was below x-axis will be flipped above the x-axis, and the rest of it will be the same. Finally, we want to graph g of x. That means accommodate for this minus in front of the blue function. So minus the blue one means the blue shape will be reflected in x-axis and we'll obtain a graph like this. So here's the final graph, the red one. That's g of x. And that was f of x. Okay, have fun with graphs.